Okay, in this lesson we're looking at Unit 6, Chapter 6, Trigonometric Identities, and we're looking at Proving Identities Part 1. We're going to be proving identities using the sum, difference, double angle, and Pythagorean identities. It's from Section 6.3 in your text, and again we're going to be proving trigonometric identities algebraically. Here are your formulas again, your double angle identities, your difference identities, your sum identities, and your Pythagorean identities. Again, all of these are going to be given to you on your public exams, so you don't have to worry too much about memorizing these. Let's jump right into a couple of examples here. The first couple of examples that I will do involve the Pythagorean identities, so let's do these fairly quickly. One strategy for proving identities is to rewrite everything in terms of sine and cosine. If I rewrite cotangent x in terms of sine and cosine, I'll get cosine x over sine x. Tan x written would be sine x over cosine x, sine x over cosine x, equals cosecant x times secant. Cosecant can be written as 1 over sine x. Secant x is 1 over cosine x. You see that the right side of the equation simply becomes 1 over sine x times cosine x. And on the left side of the equation, I got to add two fractions. The two denominators, one is a denominator of sine x, the other is a denominator of cosine x. So I need to rewrite both of these with the same denominator. The common denominator will be sine x cosine x, sine x cosine x. So you need to think about this fraction and rewriting this fraction with a denominator of sine x cosine x. In order to do that, I had to rewrite this fraction by multiplying by cosine over cosine. If I were to multiply this fraction by cosine x over cosine x, I would get a denominator of sine times cosine. So again, I'm multiplying by cosine x over cosine x. If you think about that, you're going to get a numerator here of cosine squared x. And the same thing here, in order to get a denominator of sine times cosine, I got to multiply this fraction by sine over sine. Given me a denominator that I'm looking for, sine x cosine, but more importantly, my numerator is going to be sine squared x. Now I have the same denominator, so let's rewrite this with one nice denominator. My numerator simply becomes cosine squared x plus sine squared x equals 1 over sine x cosine x. Immediately you should recognize your numerator here is the Pythagorean identity, cosine squared plus sine squared, which equals 1. So I'm simply going to rewrite the expression as 1 over sine x cosine x. And of course, that's exactly what I'm looking for on the right side. So I've now proven the identity. So we'll look at the next example here. Cosecant times cosine squared plus sine equals cosecant. I'm going to use the same approach here. I'm going to rewrite everything in terms of sine and cosine and hope that it works out for me. Cosecant is equal to 1 over sine times cosine squared plus sine equals cosecant is 1 over sine. Now I know what I'm looking for now because you can see on the right side I got 1 over sine. There's nothing else I can do with that. So I'm hoping that eventually my left side will eventually equal 1 over sine. So 1 over sine times cosine squared can be written as cosine squared over sine, of course, plus sine theta over 1. Nothing I can do here, only add the two fractions. In order to add the two fractions, I got to get a common denominator, which in this case would be sine theta. If I rewrite this fraction with a denominator of sine theta, you should recognize that in order to do that, to get a denominator of sine theta here, I got to multiply by sine theta over sine theta. And sine theta times sine theta is sine squared theta. So I've created an equivalent fraction. Sine theta over 1 is equivalent to sine squared over sine. I do have the same denominator now of sine theta, of course. And remember what I'm trying to get this to equal. I'm trying to get this to equal 1 over sine theta. And hopefully you see the answer at this point. Because when I rewrite this with a denominator of sine theta, I got cosine squared plus sine squared again. And we know that cosine squared plus sine squared is 1. So I got 1 over sine theta equals 1 over sine theta. Very similar to the first example. And I got the left-hand side equal to the right side. Okay, next example involves using your double angle identities. I need to rewrite, in the first example here, I need to rewrite my cosine 2x with something, and I need to rewrite my sine 2x with something. And I know that tan x can be written as sine over cosine. So let's do that. Now, unfortunately, I got three choices for cosine 2x, and here they are here. Sometimes it helps to look at what you're given. That may help us determine which cosine 2x we'll replace it with. The fact that I got a 1 subtract here tells me that if I can subtract a 1, I will get 1 subtract 1, which is 0. So I'm thinking I might want to use this one here, because I know that 1 subtract 1 is 0. Show you what I mean. Subtract, in brackets now, 1 subtract 2 sine squared x over sine 2x. I'm going to replace that with 2 sine x cosine x. All I did there is I used my double angle identity for sine 2a. It's 2 sine a cosine a, so sine 2x is 2 sine x cosine x. Now, my numerator is going to work out pretty nice here because I got 1 subtract 1, you see? That's why I did that, so I'll get rid of that 1. So I'm left with sine x over cosine x equals 1 subtract 1 plus 2 sine squared x over 2 sine x cosine x. Hopefully you see the answer. Pretty close to seeing it at this point. I got sine x over cosine x equals 1 subtract 1 is 0. I got 2 sine squared x over 2 sine x cosine x. The 2's will cancel, but not only will the 2's cancel, a sine x will cancel with a sine x and leave me with a sine x in the numerator. Now you should see the answer. I'm left with sine x over cosine x equals sine x over cosine x. And I've proven the identity. Okay, next example. I got sine 2x over sine x minus cosine 2x over cosine x equals secant x. Again, I want to replace my sines and my cosines here. See what I get. Sine 2x, well, we've only got one identity to replace that with, so that's pretty easy. So I'm going to use, excuse me, 2 sine x cosine x over sine x. Subtract cosine 2x. I got three choices. Now I'm going to try something. I don't know if it's going to work, but I'm looking at this and I'm thinking, I don't know. Maybe if I replace it with, I'm going to try the second one. I really don't know. And sometimes it's a trial and error process with this. And if it doesn't work, you go back and try something else. It's really that simple. Especially with the cosine 2x, because you got three options. Over cosine x equals secant, which is 1 over cosine. So I know what I'm looking for on the left side now. I'm looking for 1 over cosine x. Hopefully we'll eventually get that. Now, let's see if I can simplify this a little bit. If I look at the first fraction, I can actually cancel my signs. No reason why I can't do that. It will make it simpler for me. I'm going to get 2 cosine x over 1, subtract 2 cosine squared x, subtract 1, over cosine x. Now, if I rewrite this with a denominator of cosine x in order to add these two fractions, you should recognize that in order to get a denominator of cosine x here, I've got to multiply this with my cosine x over cosine x. That will give me 2 cosine squared x over cosine x subtract common denominator of cosine x. Now it's important that you're subtracting all of this. 2 cosine squared x subtract 1 equals 1 over cosine x. If I write this with one denominator of cosine x, I will get 2 cosine squared x subtract 2 cosine squared x plus 1. That equals 1 over cosine x. If you look closely, you see we've got this pretty much done here, because you can see that I've got a 2 cosine squared subtract 2 cosine squared. That's 0. And all I'm left with in my numerator is a plus 1. Now notice it's a plus 1 because I'm subtracting all of this. You know, when you subtract things in bracket, you change the sign of everything inside the brackets. So that becomes a plus 1, which is exactly what I wanted, by the way, because I'm left with 1 over cosine x equals, on the right side, 1 over cosine x. So yeah, I'm done. The good thing about identity is you know when you get it right, because the left-hand side equals the right side. Now we have two left. Here they are here. These are a little more challenging, okay? Certainly a fair bit more challenging. So I'll take my time going through these two. Hopefully you'll follow them. Okay, prove each identity. Sine 3 theta equals 3 sine theta minus 4 sine cubed theta. Now first of all, I'm seeing sine 3 theta. I don't have an identity for sine 3 theta. So I got to think about how else can I rewrite this that I can work with it. And immediately I'm thinking that maybe I can write sine 3 theta as, whoops, get rid of that, sine 2 theta plus theta. Now let's work with the left-hand side first, okay? Let's work with our left-hand side only in this case, because I know what I got to get on the right side. And there's not a lot I can do with that anyway, so let's leave that like it is. Let's just work with the left side and see if we eventually get the right side. So sine 2 theta plus theta, that's 3 theta. So if I'm going to use sine 2 theta plus theta, I need to use this identity here. A is 2 theta, B is theta. So I got sine 2 theta times cosine theta plus cosine 2 theta sine theta. Let's continue with that. Let's replace sine 2 theta with 2 sine theta cosine theta times cosine theta. All I did is I replaced sine 2 theta with 2 sine theta cosine theta times cosine theta plus, now cosine 2 theta times sine theta. I got three options again for cosine 2 theta, but I've given you the option that I'm going to use right here. Cosine 2a is equal to cosine squared minus sine squared. Let's see if that works. Cosine squared theta minus sine squared theta. Don't forget that's multiplied by sine theta. Looks like a bit of a mess, but I think it's going to work good for us. That's going to give me 2 sine theta cosine squared theta plus multiplying, and all I do is I multiply that together, and let's multiply this together. Cosine squared times sine, I'm going to write that as sine theta cosine squared theta minus sine cubed theta. Now let's see what I get. A little difficult to recognize, but it's a sine cosine squared and a sine cosine squared. These are like terms. I got 2 of them here and I got 1 of them here. I can add like terms and get 3 sine theta cosine squared theta minus sine cubed theta. Now I'm going to look up at my right side and see how close I am. Okay, I got a sine cubed there. Okay, that looks good. I got a 3 there, so that's looking good. But I don't have a cosine squared. Now I'm noticing that up here on the right side, I got no cosines. All I got is sines. So I got a feeling I'm on the right path because I got a sine cubed, and I got a 3, and I got a sine theta. So maybe I got to get rid of this cosine squared because there's no cosines on this side. So let's try that. Let's replace cosine squared with 1 minus sine squared. See, it's always a good idea to check what you have on the right side and see how close you are to it, and what can you do with this in order to get what you need on the right side. In this case, I recognize I don't have a cosine on the right side, so I got to get rid of that cosine. So if I rewrite it as 1 minus sine squared, will that help me? Well, we're going to see now. This will give me 3 sine theta times 1, which is 3 sine theta, minus sine theta times sine squared. Don't forget the 3. So I got 3 sine cubed theta, subtract 1 sine cubed theta. I think we're done. I get 3 sine theta, a minus 3 sine cubed, and a 1 sine cubed, or a minus 1 sine cubed is a minus 4 sine cubed theta. They're like terms. Now if you compare this with this, you see that I now have the right side of my equation. That was a little challenging. It was a little challenging because we had to realize that cosine squared had to be replaced with 1 minus sine squared. Now let's look at the next one. The next one is also a little challenging here. Hopefully I have enough room. I'll try and write small so that we can hopefully squeeze it in here. Okay, I got the tan of pi over 4 plus theta minus the tan of pi over 4 subtract theta, that equal 2 times tan 2 theta. Okay, you can see that this is the tan of a plus b and the tan of a minus b. So I need to use these two first. Let's do that. I'm going to get, using this one up here first, a is pi over 4, b is theta. So I've got the tan of pi over 4 plus tan theta divided by 1 minus tan pi over 4 times tan theta. Again, I'm just going to work with the left side for now, okay? Let's just work with the left side and see if we can eventually get it equal to the right side. Subtract. Now we're subtracting all of this, okay? Now we're going to use our tan a minus b. So I got the tan of a, which is the tan of pi over 4, minus the tan of b, which is tan theta, over 1 plus tan pi over 4 times tan theta. Now I know this is starting to look like a real mess, but it works out pretty nice actually. When you think about what the tan of pi over 4 is, tan of pi over 4, it's right here. The point associated with pi over 4 is root 2 over 2 and root 2 over 2. Tan is sine over cosine. So the tan of pi over 4 is going to be root 2 over 2 divided by root 2 over 2, which equals 1. Fortunately, that work equals to 1. So let's see if we can simplify this a little bit. I got 1 plus tan theta over 1 minus 1 times tan theta, which is tan theta, subtract 1 minus tan theta over 1 plus tan theta, because again, pi over 4 is 1. Okay, looking a little nicer at least. Now what can I do here? Well, all I can do here is I'm going to rewrite this with the same denominator. I got to add these two fractions. And I know they look pretty complicated to add, and they are. So I'm going to move this over a little bit here to the right so I can show you what I'm doing here. My common denominator here is going to be 1 minus tan theta times 1 plus tan theta. So I need to rewrite both of these with the same denominator. That's the only way I can subtract. The only way to subtract fractions is to get the same denominator. Now, here's my denominator is 1 minus tan. I want 1 minus tan times 1 plus tan. So clearly, I got to multiply this entire fraction by 1 plus tan over 1 plus tan. And I'm going to do that in different colors so you can see that's what I'm doing here. I'm multiplying by 1 plus tan over 1 plus tan. And of course, the other fraction, I need to multiply by 1 minus tan over 1 minus tan in order to get that denominator of 1 minus tan times 1 plus tan. Okay. So if I need to multiply to get that, let's see what I end up with. I got a 1 plus tan times 1 minus tan. Let's do this. 1 plus tan times 1 minus tan. Let me put brackets around that so we realize that we have to use the distributive property to do this. I got 1 plus tan times 1 minus tan. And I got a 1 minus tan times 1 plus tan. Oops, 1 minus tan and 1 minus tan. Yes, sorry. Okay. Distributive property. 1 times 1 is 1. I got a tan theta and a tan theta. It's 2 tan theta. And I got a tan times a tan, which is tan squared. Now, all I did there is I multiplied this together. 1 times 1 is 1. I got 1 times tan theta is tan theta. Tan theta times 1 is tan theta. So that's 2 tan theta. And tan times tan is tan squared. I do the exact same thing over here. And I get 1 times 1 is 1. I get a minus tan theta and a minus tan theta. Using the distributive property, it gives me 2 tan theta. So it's a minus 2 tan theta plus tan squared theta. Now remember, I'm subtracting these. So if I want to write all of this with one nice denominator of 1 minus tan theta times 1 plus tan theta, I'm going to give this my numerator. I got 1 plus 2 tan theta plus tan squared theta subtract, and you can be so careful here with the subtraction sign, because again, you're subtracting all of that. So I'm going to actually write it like this first. Subtract 1 minus 2 tan theta plus tan squared theta. Now you should see again when I subtract, I end up getting the opposite of everything inside the bracket. So let's see if we can figure out what this is going to look like. I got 1, subtract 1, that's 0. I got a 2 tan theta, subtract a negative 2 tan, which is 2 tan plus 2 tan, which is 4 tan. So that gives me 4 tan theta. And I've got a tan squared theta, subtract tan squared theta, which is 0. So I got a 1, subtract 1 is 0, and I got tan squared, subtract the tan squared is 0. All I'm left with in my numerator is 4 tan theta. Over, let's see what I have in my denominator. Let's multiply that together. I get 1, I get a minus tan and a plus tan, which is 0, minus tan squared. Okay, I think we're getting pretty close to the identities I wanted on the right side. Now on the right side, I don't think I'm going to go any further here, because I think I need to work a little with the right side now. So let's take the right side here and let's rewrite that as 2 times 2 tan theta over 1 minus tan squared theta. 2 times 2 is 4 tan theta over 1 minus tan squared theta. Compare the two. There's my right side. There's my left side. I think you'll agree that I've proven the identity. Pretty complicated, I think. But it just gives you an idea that some of these can be challenging. I'm not sure you'll ever see one that difficult on your test, but I want to throw it out there to show you the types of things you may encounter. And I think that's the last example. Yes, it is. Key ideas again. Verifying the identity using a specific value validates that it is true for that value only. Proving the identity is done algebraically, which is what we've been doing here, and validates the identity for all permissible values of the variable. To prove a trigonometric identity algebraically, separately simplify both sides of the identity into identical expressions. That's what we've been doing. It is usually easier to make a complicated expression simpler than it is to make a simpler expression more complicated. Some of the strategies that may help, and we did most of these, we use known identities to make substitutions. We did a lot of that. If quadratics are present, the Pythagorean identity or one of its alternate forms can often be used. And you can rewrite the expression using sine and cosine only. We did a lot of that. Okay, that ends this lesson.